Thank you. I just wanted to start off with a quick update on the drought, which changes from week to week in the state, even though it's been going on for 43 plus months. And among the important statistics, I think, is that for the portion of the state, say north of Midland and west of Wichita Falls, past 43 months have been by far the driest 43 months on record for that region. To provide a little bit of balancing good news, it looks like they're going to get some sustained wet weather toward the end of next week, which is probably a bit too late for many of the farmers in the area, but hopefully is the start of a wet summer. They're promising signs for the southwest monsoon. We'll see how that develops. And then, of course, possible longer-term changes in weather this winter, which we'll get to. It's my pleasure to introduce Bradfield Lyon, who I know from way back when we were graduate students at the Massachusetts Institute of Technology. I got my degree there in 1990. He got his degree in 1991, which means he knows slightly more than I do. And since then, he's been on the faculty at the University of Massachusetts at Lowell, and since 1999 has been a research scientist at the International Research Institute for Climate and Society, which is housed at Columbia University. And that institute does a lot of applied research around the world on a variety of issues, including agriculture and water. And since they discovered Texas as a whole other country, they've started working here as well. Brad?
Well, thank you, John. And thank you to the organizers for inviting me. It's indeed a pleasure to be here. And I just need to know, John, how to advance these slides. I take it I use this little guy, and one of these is probably a pointer, and okay. Yeah, the reason I graduated a year after you, John, is that I'm not as bright as you, so it took me an extra year to get my work done. That's what the... Yeah, as John mentioned at the IRI, this sort of summit that you're holding today is something that we're very much interested in. I mean, ultimately, the practical use of climate information, both in decision-making and policy. So definitely, as an institute, we really respect and appreciate what you're doing. What I'm going to talk about today is a few ideas about drought and water availability. I've studied drought in different parts of the world. And of course, everywhere the definition of drought varies. But what I've found is that sort of a universal definition that does work is that you're in a drought when your supply of water is insufficient to meet demand. And I wanted to start you off, if I can advance this, with an example actually from the Northeast U.S. in the county where the IRI, where I work, is located, Rockland County. It gets all its water resources from within the county. It's separate from the New York City water system. And certainly by West Texas standards, it's a water-abundant region. We get 3 to 4 inches of rainfall or snow on a water equivalent each month, 43 inches of rainfall on average. So you might say, what's the problem with water in this area of the country? What I'm showing here is a time series of just the precipitation variability in that county, and of course that's one of the major factors in climate. There's a lot of variability in the climate. We also sometimes are interested in look at these long-term trends. If anything, precipitation's gone up by 10%. There has been a severe drought, in particular in the 1960s, but other than that, we don't have very prolonged periods of drought in the record. So you might say, well, if you looked at these 3 data points here, you might be surprised to think that that has stimulated a discussion, actually, in the Northeast about the use of desalination to be able to meet peak water demand. And the primary reason for that is that what I'm showing here is the departure from the 100-year average of rainfall by decade. So bars going upward are wetter than the long-term average and drier, so you see the very dry 1960s drought. And population. The water supply has been basically stagnant over this period, and the population has more than doubled. The demand for water is outstripping the supply, and hence leading even in New York, places such as Rockland County to think about desalination of water. when I presented the results to the Rockland County legislature, they're asking, well, how severe is this drought? It's got to be record-breaking because we don't have enough water to meet demand. So I put together a few graphics. I'm tempted, as most climate people are, to give too much information, but basically the idea is to say we looked at different metrics of changes in precipitation, various drought indicators, and here's the duration of different droughts in months. And this is the amount, the precipitation deficit, the departure from the long-term average, so drier and longer. And so these were the droughts that triggered this discussion about desalination. When I pointed out the 1960s drought was up here, they really didn't want to talk about that. That was kind of the asteroid from space scenario that they'd rather avoid. But here in Texas, you haven't had the luxury to avoid that, as you know far better than I. I mean, here's the 2011 drought that was mentioned. I mean, when you're in beating droughts like 1956 and 34, you know that you have a severe situation on your hands. So when you do experience this type of outlier, it's not surprising here in Texas, I mean, that you have multi-billion-dollar impacts. My involvement, which has been fairly new actually in Texas water issues, is working in the lower Colorado River Basin. The goal here is to come up with seasonal forecasts of inflow to the system, and then not just doing that for an academic purpose, but to say, well, based on these inflow forecasts, how can we potentially influence decision-making to have a more efficient use of the water? But what I want to point out here is, the time series. So these are inflows, courtesy of Ron Anderson, from 1940 to 2013. So I certainly don't need to remind you of the recent low values of the inflows or the low levels of the highland lakes. But what stands out here is clearly a lot of variability in the system. Year-to-year variations. Some very high flows, some very low flows. Of course, the recent ones being most important to our current discussion. This time series is, the IPCC would say that post-1950, most of the warming on the planet is in large part due to human activities, but we don't see a large trend in the inflow here. And this is one of the problems when you start looking at climate change projections, is that sometimes the trends are very small amplitude compared to the variability of the system. It's difficult to separate the two. I'll skip over this. This is just the advertisement for our project, which is just saying we're trying to come up with these forecasts and then use them in decision-making settings. But as part of the project, what I've been looking at is the inflows into the lower Colorado, and I found that, consistent with other studies, that this is a pattern of sea surface temperatures that is consistent with low flows in the system. We're interested in sea surface temperatures because they're persistent. They tend to hang around in a particular sign, warmer or cooler, for a season to sometimes several years. And what this is showing is that low flows in the lower Colorado are associated with cooler than average temperatures here in the Pacific Ocean and warmer than average values in the Atlantic, for example. On seasonal to interannual timescales, as you know very well, La Nina is an important factor. Dry conditions are typically associated with below average sea surface temperatures in this part of the equatorial Pacific. But also on longer timescales, this pattern of cooler than average conditions on a broader region of the Pacific, and actually this whole pattern, particularly here, and warmer than average conditions in the Atlantic have been associated with multi-year droughts, such as we've actually been experiencing here in Texas recently. On the shortest timescales, on the La Nina, El Nino timescales, hopefully good news is that this is the latest forecast in terms of the probability of there being an El Nino or a La Nina this year. So these letters on the bottom just indicate the season we're talking about. So June, July, August, September. We're looking at a 70 to 75% chance that an El Nino is going to develop. A very small chance, the blue lines, of there being a La Nina. And this is consistent with many models that are trying to produce forecasts of what the state of El Nino will be. So, of course, precipitation during an El Nino year, an average El Nino year, or average across several El Ninos, is associated with above average rainfall, which is, of course, good news here, if it develops. One of the things about seasonal forecasting, is all of these things have to be probabilistic. We never know with 100% certainty that an El Nino will develop, and if it does develop, that there will in fact be above normal precipitation. It's definitely a shift in the odds in the direction we'd like to see, though, obviously, increased rainfall. On the longer time scales, as I was getting at that picture, slowly varying changes in sea surface temperatures in the Pacific and the Atlantic have been shown to favor drought. In the observations, here's records going back roughly 100 years. The current time being here, the blue bar is indicating the Pacific has been cooler than average. This is something associated with the Pacific decadal oscillation, if you will. And the Atlantic, which has been warm since about 1995. And it's this combination of cool Pacific and warm Atlantic that tends to favor drought conditions. It doesn't guarantee it, but it tilts, again, the odds in favor of there being drought. Of course, from one year to the next, there can be variations. If we get an El Nino this year, that will produce, hopefully, above average rainfall, but the overall background pattern of variation in the climate favors, at least at this point, prolonged period of drought. This result, I mean, we have a fairly short observational period, really, to look at things that are varying on decade timescales. 100 years isn't very long, but models, climate models, have been able to generally reproduce this relationship, with the key part being what's going on in the Pacific Ocean. The trick to this is that there's, at present, very little skill in predicting when these slowly varying conditions will change. When will the Pacific again begin to warm up, which would favor, generally speaking, more rainfall in the west, or a change in the Atlantic back towards cooler conditions? We don't have a good handle on that. Of course, on even longer time scales, speaking of decadal variability, tree rings or proxy climate data have been used to look at drought. Here's an example of the so-called Palmer Drought Severity Index. This red on this plot indicates drought conditions, and blue, unusually wet conditions. And so based on these tree rings, here's an example of what the estimate of the Palmer Drought Severity Index would be during 1956, the peak of the 1950s drought. So you see the dry, not only in Texas, but spreading up northern into the plains. Other years here, 1862 was a bad drought year, and even back into 1772. And in a recent study published here in the Texas Water Journal, they've extended this time series back to about 1500. And of course, the thing that stands out is the tremendous amount of variability, one year to the next. This is the zero line, wetter than average, drier than average. A lot of year-to-year variability, and the blue line represents a smooth curve there. So you see the 1950s drought standing out, but go back to the 1710s, and that was the driest prolonged period in the last 500 years. So certainly, even in absence of climate change, drought is no stranger to Texas. So, keeping that in mind, when we look at something like the climate trends, which were recently released in the National Climate Assessment, this is showing a trend in precipitation and temperature across the United States, in this case for the past 22 years. So, what stands out on the right-hand side is the preponderance of red on the map. There's a very clear warming signal across most of the United States, the most recent decade being the warmest observed in the instrumental record, pronounced warming since about 1970, but there are also regions here in the southeast where actually the trends, if anything, are flat or even slightly cooler than average, sometimes called the warming hole. Why is this occurring? Not clear. There's different hypotheses that have been put forth. One is the contribution of aerosols, which can reflect sunlight as cooling things off in this part of the world. Other people have speculated that it's conditions in the sea surface in the Pacific that we know relate to precipitation variability in this part of the world. So, for example, until about 1999, the Pacific has been unusually warm, which favored increased rainfall here and could contribute to more cloudiness and therefore cooler temperatures. Not entirely clear, not consistent with the long-term trends from long-term projections from climate change models. And if anything, if you look across Texas in the past 20 years, we see green on the map, not brown. It's been getting wetter in Texas. And if you look at even the last 100 years, you'll see a slight wettening trend in Texas. Okay? So this is the observed trend in the climate. This is looking at Texas Climate Division's rainfall variability. This is compliments of John Nielsen-Gammon. We put a 9-year, or John did, a 9-year running average through the data just to try and smoothen things out a little. But this is basically going from the late 1890s up to roughly the present time, and the different lines of the different climate divisions. And you see very large variability on these decadal timescales. Precipitation was increasing up until this point, and then declined, stayed relatively flat, increased, and then, of course, more recently, we've gone back to drier conditions. There's less variability, but the same sort of pattern, overall decadal scale fluctuations in the warm season as well as the cool season. There have been studies and theoretical ideas to suggest that the subtropical regions, as the planet will warm, will tend to dry. And in certain parts of the world, this is in fact seen to be apparently occurring, parts of the Middle East, the Mediterranean, for example. But here in Texas, we're within that latitude belt, but we're not really seeing the drying. We're seeing, if anything, a slight increase in precipitation. It's not clear what's causing this. It is not consistent with what the models are doing in terms of long-term projections. But it's also clear that there's a lot of variability in the system, and that this variability can mask slowly changing background conditions associated with climate change itself. Here's just a quick plot showing extremes taken from the National Climate Assessment. The blue on the plot here indicating that there's an increase in extreme precipitation amounts. Conceptually, the idea is pretty straightforward. That is, you warm the air, you allow it to hold more moisture. When it does rain, the rainfall is heavier. What I want to point out here, though, is that that's the overall trend. What's important in many cases is the variability in that. So what I'm looking at here is the heaviest rainfall events for this box here in the central Texas region. And we're looking at the change in the frequency of the heaviest rainfall events. And so there is an overall upward trend, but you note in recent years there's been a lack of extremes, of course, associated with the drought. And that is important for inflow to the system. So for example, here I'm looking at, in blue, the inflow to the system, in this case from February to June. And the reddish index here is an index of the extreme precipitation. The two are very highly related. The lack of extremes in recent years has actually been a contributor to low inflows into the system. Okay, finally, in terms of projections. Many climate models are used because there is no perfect climate model. If there were, we wouldn't use several models. So there's a lot of uncertainty. This is from the National Climate Assessment just released. The hatching here shows areas that there's confidence that the models are in agreement in terms of what they're going to do in terms of future rainfall. This by season, winter, spring, summer, and fall, brown being a decrease in rainfall, white being areas where we can't say anything. So you notice Texas, there's not a particularly strong signal here. Maybe parts of Texas in summer, but not very conclusive. A separate study using a updated version of the same models for different seasons, this being October, November, December, the spring season, winter, and summer, suggests drying in some seasons, not much of a signal at all, if anything, slightly wetter in the summer. The upshot is there's not confidence in either the National Climate Assessment reports or in this study, which uses 16 of the most updated models, in saying that there will definitely be an increase or a decrease in precipitation. If anything, there's a leaning towards drier than average conditions coming up. This slide I'll skip over, but we'll just say that it's not clear what will happen in the Pacific Ocean in terms of climate change. Will global warming lead the ocean to be more like El Nino, which would be good in terms of Texas getting more precipitation, or La Nina, which would mean being drier. Some models suggest drier and being more La Nina-like, others being more like El Nino. The key thing that I think is this chart on the right. The left just shows the change, according to models or several models, the change in the consecutive number of dry days, which tends to be very small in these projections. But the right is the change in extreme high temperatures, which of course are going to happen in the summertime. Depending on the emissions of greenhouse gases that are emitted into the atmosphere, there's going to be a change in these extreme days. On the left-hand side, these are non-trivial numbers on something like 14 days to more than 20 days or something. So extreme high temperatures, there's a unanimous agreement among models that's more likely to occur. This is important, of course, for places like Texas, or particularly West Texas, where we have a water-limited regime where evaporation can exceed or does exceed precipitation. As a matter of fact, in the summer, of course, the evaporation exceeds precipitation generally. So this is the problem that I see, the biggest concern with climate change in the coming, 3 or 4 decades. As John pointed out in his post here showing the 2011 drought, very dry, very warm. Basically, the scenario goes less rainfall, you dry the soil. You're drying the soil, there's less water to evaporate. The incoming energy from the sun creates higher temperatures. But at the same time, if you have less evaporation, it's more difficult to get rainfall, so the whole thing feeds back on itself. So if you get a very dry condition, which could occur, as we saw in the tree rings, naturally, the background change in the climate towards warmer conditions can exacerbate the drought. So it's going to lead to additional heating, which leads to additional evaporation and higher temperatures. In a recent study that John was a co-author on, it's estimated that about 1/5 of the extra warming here, if you will, was associated with long-term climate change, but little could be said about attributing the precipitation change to anthropogenic causes. Quickly, because I know I'm running out of time, I just want to say, here's a study that was done here at the University of Texas back in the 80s, but a classic study. They looked at 3 water systems, small, medium, and large. And they noticed that there's these thresholds in terms of water use. As temperature is below about 70 degrees Fahrenheit, water use doesn't change substantially. But you hit about 70 degrees Fahrenheit, and it increases more dramatically when you hit 90 degrees. So, of course, with climate change, if you shift temperatures towards warmer conditions, it's much more likely to have extreme high temperatures, and therefore the higher water use. Okay? Here's just an example of that from Austin's website. So basically, in conclusion, in terms of the next 40 years, natural variations in the climate system are going to be the dominant source of variability in the water system. On seasonal to interannual timescales, this includes importantly, but not exclusively, things like El Nino and La Nina. Decadal timescales, I mentioned conditions in the Pacific and the Atlantic. And it's not just the total amount of precipitation, but the character of precipitation. The lack or occurrence of extreme rainfall events are very important. In terms of climate projections, it is very likely that average temperatures, as well as extreme temperatures, will increase. So this will intensify heat waves and droughts that will arise naturally due to natural variability. There's much more uncertainty for precipitation. Models generally favor drying. I've seen one study that suggests by the mid-century, yes, that maybe a 5% decline, but there's large error bars on that. And of course, summer is the key season because that's when evaporation is at its highest point. And as you know better than I, that particularly in Texas, it's a water-limited regime, so evaporation is already exceeding precipitation. When climate change and climate variability act in the same direction, climate change trying to make things warmer, if you naturally have a drought which makes things warmer, you're going to lead to more extremes. I think that's straightforward. And by itself, climate change is pushing the system towards increased water stress, primarily due to increased evaporation associated with high temperatures. So I'll leave it there, and I apologize for going a few minutes over. Thank you.
Thanks, Brad. We do have time for a few questions, so stay up here. Yes.
Yes, if you did a trend, you would find very little, essentially no trend.
Okay, so the question I have is, obviously, trees and vegetation provide kind of, they act as kind of a capacitor for water, right? So their root systems can absorb and release water as needed into the system. And the question is whether these inflows take into account this vegetation at all, inflow calculations, the fact that the water goes in it, and whether these are factored into the climate models at all, whether you're able to factor that into that. It acts like a kind of capacitor to the system, and it can absorb, naturally absorb and release water.
Well, in terms of the time series that I showed, that's the observations. I mean, it's...
Repeat the question.
Oh, I'm sorry.
Please, if you would, you could ask the question something on the microphone.
Yes, sorry. The question was essentially, does the time series that I showed for inflows to the lower Colorado system, is that take into account effectively vegetation and how it can influence the inflows? And the answer is yes, in that these are the observed values. So there's not a model this is going into. This is what the observed inflows are. There's the one caveat. I mean, I'm not a water specialist, but Ron Anderson, who put this together, I mean, they normalize the flow to take into account the fact that there is several dams, of course, along the waterway. The second part is, in terms, the question was, well, do models, I guess climate change models or land surface models, take this sort of thing into account? There are different types of land surface models, some that are more sophisticated and do try to take that sort of thing into account. The large-scale climate models do have a crude land surface model in them, but it wouldn't capture faithfully, I'm sure, the degree to which the things you're talking about go on in this particular watershed.
Yes, thank you. My name is Jordan Fernandes. I'm a consulting engineer within Terra, and I've done a lot of work studying the Lower Colorado River Authority and their actions. And I just have an overall question. I mean, I make all these models too, and I try and calculate what water is likely to be available in the next few years. And the general gist of it is we just can't calculate with any sort of accuracy. So can you comment on what you think would be necessary to manage the available water that we have during such drought conditions, rather than looking at the past and assuming the past is going to repeat itself in the future or anything different? Really, I'm looking for an idea of how we best manage the water that we have and might be able to plan for.
Well, when it comes to management, so I'm a climate scientist, not a water specialist, so I think the discussions that will take place, I guess, today will address that. I don't have specific ideas about, how we could better manage the water. There are different techniques that we're trying to use. I agree with you. It's not by any means a trivial problem to come up with forecasts. We're trying to incorporate different types of combining observations with what climate models predict on the seasonal time scale, where we have, in many cases, more confident. But yeah, we're hoping to get something better than, if only by a little bit, than saying this is what's happened in the past and that's the best that we can say into the future. But we'll definitely be happy to share what we find along the way in that regard.
Thank you.
Thank you.
This might be a little bit of a follow-on, sorry. Bridget Shea, I'm the Democratic nominee for the Travis County Commission, and I've been working on water-related issues for 25 years. I'm concerned that these newer projections aren't yet making their way into the water availability modeling and the long-range forecasting that we're doing for how much water will be available and how we allocate it. on our river authorities and elsewhere. Do you have a sense for if that's the case? Are they incorporating more of this as quickly as they can? Or I know there's an official policy at the state level that it's not happening, so I'm not sure how that then can be incorporated into their long-range water planning.
I can't speak to, I'm simply not aware of the extent to which locally people are trying to incorporate that, the projections into specifically water within the system. But this is something that certainly people are doing in different parts of the world, like the upper Colorado River. Having said that, I mean, the problem is that there's a large degree of uncertainty, and you have to include that in your models. What we advocate at the IRI is not coming up with an answer to say, like, climate change will lead to a N% increase or decrease in flow. It's trying to say, like, what's the best estimate of the range in flows that we can estimate coming in the next 50 years or something like it. So people are doing that. It could be applied locally, but as I showed in terms of the precipitation input, there's a lot of disagreement among the models as to whether it'll get wetter or drier. So it's similar to the seasonal prediction for the lower Colorado, that it's not clear what that ultimately the signal will be. I'm not saying it shouldn't be done. I think it's a good experiment worth trying just to see what will come from it. But
Thank you.
I hope that helped.
Okay. Dave Lindsay, Central Texas Water Coalition. I'm a chemical engineer coming out of industry and have been looking at the lower Colorado River for a few years and bringing statistical process control. Looking at that, you're actually able to see, using your actual data, a shift. And the industries used that to be able to predict when you did see something that had changed. Is there what's the chance of getting SPC brought forward and used more in the modeling so it helps us understand it indicated Dr. Nielsen-Gammon's point about what something changed, the AMO, PDO alignment is kind of consistent. Just thinking through, does that kind of SPC, is that being kind of on the horizon of maybe being used to help us be more predictive?
Yeah, there's different techniques. So in this particular project that I'm showing that I'm involved with on the lower Colorado is working specifically with two water specialists who are familiar with many different kind of statistical techniques. So we're going to exactly use any tool that we can to try and tease out as much predictability and different aspects of the flow. If we see shifts and things like that, that's definitely something we'll be looking.
One of the nice things about SPC, it gives you control limits. You know when the process changed. It can also help you understand when the process changed out. There are upper control limits, so that would allow us to know when we got enough water to start to say things have changed. So there's some advantages to that. Anyway, thank you.